Now let us see some selected questions from the exercises. Now one question is, show how the following alcohols may be synthesized from appropriate alkenes. Now one example is given. Say cyclohexyl methyl alcohol may be called 1-methyl 1-cyclohexanol. It's a tertiary alcohol. The OH group is down the plane and CH3 group is above the plane. And suppose a mirror is placed along the dotted line, and the mirror plane passes through CH3 and OH. These 2 points, CH2 group here and CH2 group here, they come as object and image groups, so we say they are equivalent. So the carbon to which OH is connected is named alpha carbon and then beta dash carbon. Then there is a beta carbon here. So double bond may be formed between this alpha and beta dash, or alpha and beta. So between alpha and beta there is a double bond in structure 1, and in structure 2 between alpha and beta dash the bond may come here or here, the same. So 2 structures. Now the carbocation obtained from 1, an H positive may come here, so this pi bond may shift in this direction towards H positive, so we get positive charge, and this carbocation is a tertiary carbocation. Now equally well, the H positive may come here, the pi bond may migrate in this direction, and we get a positive charge of this carbon, that is a primary carbocation. Now the carbocation obtained from structure 2, we can have a positive charge here or a positive charge here by absorbing an H positive on either side. So when H positive comes here, we get positive charge here. When H positive comes here, we get positive charge here. So 2 structures. Now this is a secondary carbocation and this is a tertiary carbocation. Now secondary carbocation is more stable than a primary carbocation, and if you want exclusively this product, we should take this one because this is the least stable, so there is no chance for formation of this compound, but there may be a slight percentage of this compound, but this structure can give a slightly more percentage of the alcohol, so better choose this one, which will give mainly this tertiary carbocation and very minute amount of this less stable primary carbocation. So answer may be this one. Now then a second example is given. There again we have a mirror plane passing through OH and CH3 bisecting this molecule, so that this point and this point called beta dash are equivalent, and there is a beta position, and then alkenes forcible are between alpha and beta dash, this one, between alpha and beta, this one. Now as usual, if H positive attacks here, we get a positive carbon here, and that is a primary carbocation, this one, and this is least formed, so prefer this one for a preparation of this alcohol. Now again coming to a third example, as in the previous cases we have alpha carbon here, and this is a beta carbon, this is another beta carbon, this is a third beta carbon. Now when the pi bond is between these two carbons, or between these two carbons, or between these two carbons, we get three alkene structures, but the one between these two carbons will give a primary carbocation, that is this one, which is least stable, and so there is least chance of formation of the carbocation. So to get this product to a large extent, a high percentage, and synthesis involve the formation of a product in a higher yield, higher percentage, this alkene is preferred. Then another question, when 3-methyl butane 2-ol is treated with HBr, the following reactions take place, give a mechanism. 3-methyl butane 2-ol, the parent is butane 2-ol, you write 4 carbon atoms in a chain, number them 1, 2, so here numbering should be done like this, 1, 2, 3, 4, because the functional group is connected to the carbon possessing the least locating number. Now the reaction is addition of H positive first to OH group, and the product expected is this one, that is bromine is not getting connected to this carbon but this carbon. Now first of all, H positive adds to OH giving OH2 positive. It's a first reversible reaction because OH group is less basic. And in the second stage of this reaction, the compound undergoes what is called a rearrangement. A rearrangement means the relative positions of atoms are changed, or simply the position of atoms are changed. Now what happens is that the OH2 group takes up this pair of electron, so this bond is diminished, this pair of electron is getting into the orbital of oxygen. So when one bond is removed, the valency of carbon becomes 3. To maintain its valency to 4, the hydrogen with this bond will be migrating to this carbon. So hydrogen with this bonding electron pair will be migrating to this carbon. Then the valency of this carbon is maintained 4, but the valency of this carbon becomes 1, 2, 3. And since during migration this bond as a whole is moving, the share of electron of this carbon is being lost. So this carbon attains a positive charge. And this CH becomes CH2. Now suppose there is no migration here. When this OH2 group is removed, we get a positive charge here, and this carbon, positive carbon, is directly bonded to other carbons. We call it a secondary carbocation. Now when hydrogen with its bonding pair of electron migrates, we get a tertiary carbocation which is more stable than a secondary carbocation. So this migration is called sometimes called a 1-2 shift. And here hydrogen, since it is taking up both the electrons, we expect a hydride ion. This hydride ion is never free. It first of all gradually withdraws this bond from this carbon and gradually forms a bond with this carbon. So At the same time, the hydrogen will be bonded to this carbon by a partial bond and this carbon by a partial bond. So, and that's a slow process. So migration occurs like that. H minus is not free. It's not obtained as a free ion. It's called a hydride shift also. So 1,2 shift, because this carbon is 1, then this is 2. Rearrangement, hydride shift, 1,2 shift, etc. We get a more stable carbocation, and this is a slow process because this is a bond breakage process, and again this involves bond breakage and bond formation. Overall, the reaction is slow because net reaction is a bond breakage. And so step. Now then, this carbocation is attacked by Br negative in a fast step. So the reaction involves 3 steps. First, the reversible process, that is absorption of a proton by OH group. We get OH2 positive. The reaction is reversible because OH is not a good base. So the species can get reversed back to the free alcohol and H positive. It is fast reaction. Then there is rearrangement, 1,2 shift or hydride shift. It's a slow process because net reaction involves breakage of CO bonds. We get a tertiary carbocation which is more stable than a secondary carbocation. Then in a fast step, the bromide ion attacks the tertiary carbon center. Now then, another question from propan-1-ol, how will you synthesize 1-propoxypropane? What is 1-propoxypropane? Now 1-propoxypropane, you number this carbon 1, 2, 3, and on 1 we have propoxy group. So it is called 1-propoxypropane from propan-1-ol, and this one is propan-1-ol. First of all, react it with the sodium metal. Alcohols are acidic. It's slightly acidic, not so acidic as phenols. A very basic metal, sodium, will react with alcohol producing hydrogen and its sodium salt. So it is sodium propoxide. Sodium propoxide. Then we have to prepare an alkyl halide, a propyl chloride from propanol, reaction with SOCl2 or BCl5 or HCl and anhydrogen chloride. Any reagent may be used. Now, advantage of SOCl2 is that the byproducts are gaseous. Sulfur dioxide and HCl gas may easily be removed from the reaction mixture. Then OH is replaced by Cl. You combine sodium propoxide with the propyl chloride, then Williamson synthesis of either. NaCl is removed and we get propoxypropane. Now name the reagent and the equation for the preparation of 2-methoxy-2-methyl propane. Now here the structure of the product has to be written first. The parent of 2-methoxy-2-methyl propane is propane. So you write 3 carbon atoms in a chain, number them 1, 2, 3, and on carbon 2 you connect methoxy first, methoxy, and again on carbon 2 connect methyl. So it is an ether where the alkyl groups are one a tertiary alkyl group, tertiary butyl group, and another a primary alkyl group, that is methyl. So the alkyl groups are tertiary alkyl and methyl. Then there are 2 choices. First you take the alkoxide of tertiary butyl group. So tertiary butyl alkoxide is taken, sodium tertiary butoxide. Then you take the alkyl halide, methyl chloride. So tertiary butoxide and methyl chloride, NaCl is removed and you get OCH3 bond, this compound. Now you can start with the tertiary butyl chloride, and then ONA is connected to this group with sodium methoxide. Then you will be getting an alkane because this tertiary butyl chloride undergo ionization to give tertiary butyl carbocation, and since sodium methoxide is a good base, it will be taking up a proton from this methyl group, and H is removed as H positive, so that the CH bond will be shifting in this direction. The positive charge getting neutralized over carbon, and so we get the alkene as the main product. So you prefer this parts. Then some conversions, propene to propan-2-ol. Symbol, propene is CH3, CH double bond CH2, addition of HCl, negative part going to carbon having lesser number of H atoms, Marconi-Clausen rule. Then sodium hydroxide, Cl is replaced by OH, removal of NaCl, so simple reaction. Then heavily convert CH3, CH2OH to CH3OH, and here it is descending a series, means decreasing the carbon number. One CH2 group is lost. Now for this, this molecule has to be converted to an alkane, and on heating with aluminum oxide at 250 degrees Celsius, water may be removed. You can use concentrated sulfuric acid at 443 Kelvin or a phosphoric acid. So dehydration reaction, we get the alkene ethene. Then subjected to addition of ozone followed by hydrolysis, the net reaction is breakage of this bond and addition of two oxygen atoms here, CH2 double bond O and double bond O. We get two molecules of formaldehyde. Then this formaldehyde is subjected to reduction with the lithium aluminum hydride. Then what happens is one H comes here, one H comes here, and we get CH3OH, so addition of two H atoms. Then conversion of benzyl chloride to benzyl alcohol. See, benzyl chloride is this one, and you neglect this benzene ring. This is something similar to an alkyl halide, so it can undergo easy reaction with NaOH, and NaCl is removed and CH2OH is formed. So this part is acting like an alkyl halide, so you get benzyl alcohol. Now ethyl magnesium chloride to propan-1-ol, CH3 CH2MgCl to CH3 CH2 CH2OH. This is a primary alcohol, and a Grignard reagent can give a primary alcohol only on reaction with the formaldehyde. So ethyl magnesium chloride is treated with formaldehyde, CH2 double bond O. It may be written as HCHO, that is HCH double bond O, or CH2 double bond O. So addition reaction, CO bond is polarizing like this, and the Mg magnesium, it's a metallic part, it forms the positive part, and this alkyl part becomes negative, and the C becomes positive, so that this CH3 CH2 is getting connected to this carbon, and MgCl positive part is getting connected to oxygen. And then we get the addition product, and it is subjected to hydrolysis in acid medium, chemical reaction with water. Again here Mg is the positive part and O is the negative part. Water splits into H positive and OH negative, so OH, MgOHCl, we get CH3 CH2 CH2OH. So for a preparation of primary alcohol from Grignard reagent, always we select formaldehyde, and if an aldehyde other than formaldehyde is used, we get a secondary alcohol, and if a ketone is used, we get a tertiary alcohol. And this example, methyl magnesium bromide to 2-methyl propan 2-ol. You write 3 carbon atoms in a chain number 1, 2, 3. On carbon 2 you connect methyl group, and on carbon 2 propan 2-ol you connect OH group. So we get a tertiary alkyl group here. So this is a tertiary alcohol. So use Grignard reagent and a ketone. Always a ketone gives a tertiary alcohol. Now which ketone is to be selected? Now you consider this molecule. There is one methyl group and there is one methyl group in the Grignard reagent. So this methyl group might have come from the Grignard reagent. Then the remaining part is COH, CH3, CH3. So this should come from a ketone. And this hydrogen is obtained during hydrolysis of the Grignard reagent. So H is obtained from water. So that the remaining part CH3CO, CH3, the corresponding part is CH3C double bond or CH3, a ketone, that is called acetone. So that the Grignard reagent should react with the acetone. So CH3MgBr plus CH3CO, CH3. Addition, alkyl part getting connected to carbon. Alkyl part is negative here, Mg positive, MgBr positive, going over to oxygen, OMgBr, then CH3 connecting this carbon. You get this particular addition product, which on hydrolysis OH and MgOH. Now ascending an alcohol, we have seen this method earlier. I am just repeating this. For a conversion of CH3OH to CH3CH2OH, CH3OH plus PCl5, you replace OH by Cl, then potassium cyanide, you get CH3CN. Hydrolysis of cyanide we have seen earlier will give carboxylic acid, then this acid can be reduced to CH2OH, COOH can be reduced to CH2OH using lithium aluminum hydride. So much about the conversions and exercises. Now coming next to the case of aldehydes and ketones. If you have got any doubts or suggestions or questions, you may please put these in the comment box so that I can see and clear your doubts and your answers to your questions if I know the answers. Thank you.